we're talking about solubility products, and maybe I'm sure you've heard of the greenhouse effect, and a lot of it is a solubility problem. What I think is really interesting about the greenhouse effect is over the past, from 96 to 2014, average temperature, this is the big news that's coming out now. Look at the temperature, the global temperature, flatlined, right? So there's no global warming. There is no global warming, right? Have you heard any of this? Have you heard any of this? But look what they're doing. You can't do that with data. Take out the little section that you want, right? Let's just look at this little tiny little section right here. And don't look at anything else. You can't do that, right? Where's the Q test in that? That's totally thorough. You can know. So it's a real issue. There isn't a climatologist on the planet that doesn't believe in the greenhouse effect. Do you know what the real fear is of greenhouse effect, by the way?
You see the 400 parts per million carbon dioxide in the atmosphere now? Changed this spring.
Yeah?
It's officially hit 400 parts per billion.
Yeah. But the temperature's staying relatively constant, though. And they think that has to do with El Nino and stuff. But anyway, the point is CO2 they believe is a big issue. You make all the changes you need to, right? Everyone goes solar, right? And this whole thing, will this level off immediately?
No, it
It takes
takes like 100 years.
100 years. It's going to keep doing this for 100 years. And then it's going to level off. CO2 is such a light gas. That's how long it takes to get rid of it. And it's a solubility issue, too, and supply. And so anyway, that's our world. Okay, writing solubility product KSP expression. Is calcium, I changed this already, so changed it this morning, Albert, so that's just how life is, right? So is calcium sulfate soluble or insoluble? And how would you know, Albert? Calcium sulfate, soluble or insoluble, and how would you know? Look at the chart. Where is sulfate? Oh, there it is. You see it? Very bottom. Okay. So what would you say? Is calcium sulfate soluble or insoluble? It looks like it's under the soluble listing, but you got to check the exceptions. Is calcium in the exceptions? No. So that means calcium sulfate is soluble, right? All sulfates are soluble except for strontium, barium, and lead and mercury. So that means it's got to be soluble. So does that mean if it's soluble, what subscript do I put on it? AQ. Okay. AQ. In the question, what is the solubility of calcium sulfate, Jamie? What's meant by solubility? Well, if it can dissolve in water or not would be, is it soluble? But if they say, what is the solubility? It's how well it dissolves. In fact, what is its concentration in water? That's really what solubility is. What is its concentration in water? Okay, of calcium sulfate. Is that possible, by the way? Look at these insoluble things. Carbonate and metal cations, like calcium carbonate. Dang, that should be a solid. Does it have a concentration in water? Is that possible? It's insoluble. Right? It was a yes-no answer in Gen Chem, but now everything dissolves a little tiny bit. So, yeah, it dissolves in water. Very, that's what makes it a chemistry problem. That's what makes it, hey, we can calculate solubility. You can't calculate solubility of salt, sodium chloride, because it totally dissolves. There's nothing to calculate. Whatever you dump in dissolves. But calcium carbonate, whatever you dump in, it looks like it all stays there, but some of it dissolved. How much dissolved? Solubility. You got to calculate it. Exactly. There's all the metals in there. Okay. Shoot, I forgot it. I'll be right back. It does, to a very small degree. And some of them to a larger degree. They vary. And that's what the issue is for today. All right. So here I put some calcium hydroxide in water is what I did there. Okay. And look, it's not dissolving, right? It's definitely, what's the word? Saturated. I mean, if anything dissolved, it totally quit by now. It's at equilibrium. Do you have to have a saturated solution to measure solubility? Daisy, what do you think? Do you have to have a saturated solution to measure solubility? Yeah? All right. I can measure solubility. I guess, what do you think of as a saturated solution? Do you have to have a solid present for you to have a saturated solution? Right? Couldn't I just filter this out and then take they call it the supernatant, take that liquid? Is that still a saturated solution? Yeah. So, but technically, you have to have a saturated solution, otherwise solubility doesn't make sense. Right? You got to have you really need the solid there. And you'll see why we haven't got there yet. But you need a saturated solution, otherwise solubility doesn't make sense. Because there's only one answer for solubility. If you don't allow it to reach equilibrium, well, then the answer is going to be all over the place. It's going to be starting out really tiny bit of calcium hydroxide. Over time, it might grow a little bit. It'll max out at solubility, but where do you stop? So no, it needs to be saturated for you to calculate solubility. Otherwise, the calculation won't make sense. The solubility product constant, or the equilibrium constant for solubility reactions, has what symbol? Anyone recognize it? It will be what? It's in the notes already somewhere. KSP. What does the SP probably stand for? K. Solubility product, exactly. Now we need to have a convention for writing all solubility reactions. Right? It's always going to be what going to what? Where do you write the solid? You got to write the solid. You got to write, exactly, you got to write that solid as a reactant every single time. Otherwise, you're never going to get the right answers. Because remember, these numbers are tabulated. And they're tabulated according to how you write the equation. You got to write the equation their way. The solid going to its ions. Okay. So, well, that's what's coming up right here. What is the solubility of calcium hydroxide? So how do you do this calculation? Yeah, because KSP will be products over reactants, right? And we can write our equation, solid going to ions, but still we don't have the question answered, what is solubility? So what ions would it go to? Good, Ca plus 2 and excellent, 2 OHs. Okay, and we can write the KSP, doesn't hurt. But it still doesn't help us. What number? 5 times 10 to the negative 6. That has to equal calcium hydroxide. It's good practice. Squared all over. Well, 1. Right? Because solids. Products over reactants. Notice you got to square the hydroxide. So we can write all this stuff, but it doesn't answer the question, what is solubility? How do you get that? What is it? Solubility is the X in what? Solubility is the X in ice. Solubility is the X in ice. We're going to be messing with ice. Now, see if you remembered this ice thing, Matt. Okay, what was I? What was I?
It was a long time ago, Dr. Smith.
That's fine. It starts with an I. Initial. C, everybody, was change. E was equilibrium. All of your answers are in the equilibrium row, right? 'Cause that's what we're after all the time. If there's anything there initially, you put it in the initial row. Otherwise, you just put dashes everywhere, right? What and what never show up in K expressions? Solids and liquids. So if you ever have, if you're ever doing ice and you have a solid or a liquid present, it can't show up in your KSP expression. So just put dashes everywhere. If they would have said there's 20 grams of calcium hydroxide solid initially, you don't care. It's a solid. It doesn't show up over here. We just wrote it. So you put dashes everywhere for solids. You look at the question. Is there any calcium ion there initially? Initially. No. Is there any hydroxide there initially? No. What would it look like if there was hydroxide there initially? What would they say, though? How would you word that in the question?
What is the solubility of calcium hydroxide?
Yeah, what is it? Yeah, good. What is the solubility of calcium hydroxide?
And hydroxide.
In a solution of, what could you put with hydroxide and make it soluble? Sodium. Any group 1. You're going to see that a lot. That's the only way they can get you to put something in that initial row. In 0.2 molar potassium hydroxide. Then you'd put a 0.2, or would it be a 0.4 right here? What would it be? It'd just be 0.2, because 0.2 is the concentration of hydroxide, so it's 0.2. So you would put a 0.2 there. But that's not our question, right? But that's what would happen. So let's see if we can finish this. What do you put in the change row now? All right, plus x's and minus x's. Now these x's are on the product side, so are they plus x or minus x? Plus. They're forming, right? They're forming, so that x is positive. Plus x and, I should put my plus sign. 2x. Yeah, that's coming up in the homework, just so you can handle it. Okay, and then you add up the initial and the change, and you get your x and 2x. And then what do you do? Put that in the KSP. Because remember, solubility is the what in ice? X in ice. All you're after is x. So you just substitute it in. You should write that, all right? Solubility is the x in ice. Okay, so KSP, which is 5 times 10 to the negative 6, has to equal what over what? What did you write, Javier? Yeah, we don't need concentration, though. We'll just put x. So you're just putting x in for calcium.
2x.
And 2x over 1. Everybody agree? Yeah, it's 2x squared. So it really helps that we wrote this first. It really does. Right? Because hydroxide, the concentration of hydroxide is what? 2x. Whatever x is, multiply by 2, and you've got the concentration of hydroxide. What are the units of x probably then? Big M. Molarity. Good. So hydroxide is 2x. Calcium is x. Do some math. What do you get? You get 4x cubed Divide that by 4. If you don't have cube root on your calculator, you could raise both sides to what power? Anybody know that game? The third. 5 to 10 to the 6. Divided by 4. Yeah, so I got about 0.011 or so for my x. Hopefully someone else got that. Did you get 0.011? Shit. Really?
I did 5 times 10 to the negative
6. Divide it by 4. Then take the cube root.
raised to the 1/3, right?
Raise to the 1/3, or oh, I bet I cubed it.
Yeah.
No, I get 0.01. I don't know. Something's wrong with that. You should get 0.01. 0.011.
Yeah, 0.017.
Yeah.
0.008. I have no idea. 5 second E negative 6.
Okay.
Divided by 4.
So make sure you can get that.
Oh, dude, when you yeah, dude, when you raise it, the exponent, you gotta put it in 1/3 or it's like doing
Yeah, I use a lot of parentheses on that calculator. That's true. On that one, you can do it two ways. You can do 5 times 10 negative 6, divide it by 4, hit equals, and then you can find the cube root button. It's yellow. Or you could do the x to the 1 over y button. That's yellow too. And push it to the 1/3. But the cube root button is probably easier.
So the solubility is the x.
Solubility is the x.
And we'll use that in the final concept.
So that is our answer.
No.
That's x is what we're after. X is the solubility. Okay, that is our answer. Okay. There's usually a complication with solubility, and I don't know what their tradition is. Do you remember this? What units do they like in solubility questions? This is a way back when. Man, if you remember this, you're doing really good. They liked solubility. Find solubility in grams per, I don't know why. It's just a traditional thing, and it's in the homework. So how do you convert? It's still to X and ice. You still have to do everything we just did, but you have to convert big M to grams per liter. There you go. 0.0108. That's moles of what over liters of what?
same hydroxide.
Moles of calcium hydroxide per liter of solution, right? So you're right. You just got to find the molar mass of calcium hydroxide, and you got it. So it's not too bad. And then you get your answer in grams per liter. Okay? So it's not too bad. But they do that a lot for some oddball reason.
But we won't have to do it per test, right?
Oh, I think you see what's coming up here? If you scroll way down, you have a handout. And I bet you, there it is. Look at that. Grams per liter. So this is part of the homework, I'm sure. Okay. But so you'll have to tear that out and turn it in, right? But let's get there first. Let's get there first. So on this 6-D, because we need some background information before we're ready for that handout. Which will be more soluble? Barium iodate or calcium? Or calcium iodate. What would be more soluble? You need a game plan for this. Eustacio, you have a game plan for this? Where'd he go? He's not here. Let's ask Alyssa then. Which would be more soluble? She does calcium iodate. She's got a 50-50 shot at this. Now, if you're just going to guess, why is calcium iodate the best guess?
Bigger KSP.
Bigger KSP. Because KSP is products over reactants, and products are what? The solid or the ions? The ions. So the bigger that KSP is, yeah, it's going to be more soluble. But here's the complication. You look at those dang exponents, right? Is that going to screw stuff up? Right? My guess is if you had barium iodate and, I don't know, what would be what +1? What is a common +1? Maybe scandium iodate? What's one of the +1? Copper has a +1. Copper iodate. If you're going to compare these two, let's say you had KSP and they gave you some number. Compare these two. Then I don't think you can go by KSPs at all, because those exponents are going to screw everything up and getting you, because you have to get your X, right? Because X is solubility. You have to get X for barium iodate, compare that to X in ice for for copper iodate, and see which X is bigger. That'd be the most soluble. But when they have those exponents get in there, that's going to mess things up. So I think when you look at, when they're in the same format as this, you pretty much have to solve the question to make sure. But see how the exponents should be the same, right? It's the same format for both. I think you can just look at the KSPs. Would be my pretty firm guess. Otherwise, you can't. You recognize that? You can't look at KSPs if you're comparing just those two. Does that make sense? So there's no easy way out. You got to find X in both cases. Easy way out here, same format. So just pick calcium iodate. Okay. So let's see if you can see how to do this stuff here. Let's try this one. You need a KSP for it. Where's a KSP for that stuff? I wonder if I have a table of these things. So go ahead and get started. You're going to need to write the X and ice and stuff. I don't have it. I'm going to have to Google it. The copper bromide. (6.27 times 10 to the negative 9). I should have had that in there. Okay, that's your KSP. 6.27 times 10 to the negative 9. And you're after the concentration of the copper ion, copper 1. If you think you have an answer, go on to part B. Bless you. Anybody not sure where to start? All right. Pretty much just write the solubility equation, right? Do ice. Look in the equilibrium row for your answers. And whatever's under that copper 1 ion in the equilibrium row, that's your answer. Just have to find it. Yeah. Yeah. And then products over reactants. So it'd be x squared all over 1 has to equal this. Find your x, and that will be the copper 1 concentration. With units, you need units. They don't care. They don't care, so just leave it in big M, right? Since they don't care, leave it in big M. Javier got about 7.9 times 10 to the negative 5. Okay, good. A lot of people are getting 7.9 times 10 to the negative 5 for the concentration of copper. And then try B. That number, see if it makes sense. That number should either go up or down, that 7.9 times 10 to the negative 5. That's Le Chatelier's principle in action. Yeah. Alrighty, good. Well, it won't be 2x. It's going to be x squared. Because x times x is x squared. Yeah, because you'll put an x here, you'll put an x there. Good question. I forgot about that. There's a trick to doing that. You can use a quadratic equation, but there's a but. You don't need to if it meets a certain requirement. See if anyone remembers why. Oh, sorry, not that. Ah. Okay, wouldn't it be nice to be able to jump from, did you get this far? You see, it's important to see how I got this far, right? I set up the solid going to its ions. I put in the initial amount for the bromide, and then changes x, right? Hey, if there was a 2 here, just to make sure you guys can play this game. If there's a 2 here, how would that change the ice table? 2x. And that 2x would go here. It doesn't change the 0.1. Okay. Anyway. So then we wrote KSP number, products over reactants. And then, ooh, I dropped this x. Right? There was a rule. Right? If you want the real advantage for having these equilibrium constants being extremely small. This is a billionth, right? For every one product, there's a billion reactants. It's negligible. So it's very, very small. The point of having this means that there's going to be a lot or a little bit of these products. Extremely small, right? 1 out of a billion. So X times X plus 0.1 has to equal this. X has to be extremely, extremely small. Nowhere near 0.1. So you just say 0.1 plus X, 0.1 plus a really small number is just 0.1. That's what the approximate means. And then you just go solve it and see if it actually worked. X is going to be what? 6.27 to 10 to the negative 8?
But if it's bigger than
So it is really, so it worked. So the question is, when can you do this?
When it's more than -5 or less than -5 exponent.
less than negative.
Yeah, it just, the guess, like here we got our answer of, what did you say it was? 6.27 times 10 negative 8? Okay, there's our answer. And it's not, technically it's not correct because it's off by, I don't know, it might be 6.2699999, right? But it's really, really close, good enough, right? And the bigger this the smaller KSP gets, the better off we are at making this. The bigger KSP gets, the worse our approximations get until they finally get unacceptable. You have to do the full quadratic. You have no choice. So where is that cutoff? It's argued. I mean, you should really never do it, right? If you want to really be anal. But come on, who's going to write 6.26 and about 8 nines and then that ain't going to work? So when is it practical? When it's practical is somewhere around the -5 maybe. That's where things are getting, you better be careful, right? -4, -3, they say don't even, never drop X's. So it's questionable. Like around the negative, I'm talking about this answer, this number right here. This 10 to the -9. When that gets to be 10 to the -5, well, I don't know. It's questionable. That means it's really important to go back and check your answer. Is this number a lot bigger than my X? Then you're okay. It's all the more important to check it. So, I guess Smith would be having a really bad day if you see a quiz and it has a KSP with 10 to the negative what? 4, 5, or 3. Forget it. You have to do full quadratic. Okay? Make sense? But if you look at these KSPs, almost all of them, that's why they're KSP problems, because Ks are so small. So it's rare that you need to worry about it. Maybe 1 out of every 10 problems or something. Okay. We're almost out of time here. I'll just solve this one, then we'll call it a day. Find the concentration of copper in a solution saturated with, well, this big honkin' compound if hydroxide is fixed at 1 times 10 to the -6 molar. And they give you the KSP. So this big complex ion there. Find the concentration of copper. What I mean by fixed is application-wise, they just have a buffer, and the pH is fixed. Mathematically, wherever you see hydroxide, you put in what number? Yeah, 1 times 10 to the -6. All right, so start out, pretty much you have to do ice, right? You don't have much choice in this. See, it's possible to have fun and analytical. You're Kevin. I don't know how you want to represent this. I don't know, because it's fixed.
Does the 6 coefficient still go on that? Is it like get distributed to that value?
Good question. Should this be 6 times 10 to the negative 6?
I was thinking, yeah.
Or
do we raise it to that?
right? We can. Let's do it. Let's not erase it. Let's just do this, because I'm jumping ahead. You should have 1 times 10 to the negative 6 there. You should have a 6x. And you should have a 1 times 10 to the negative 6 plus 6x, right? If you want to follow everything we've been doing. And then substitute into the KSP expression. But this whole thing. Right? So you kind of don't worry about the 6x because it has to be 1 times 10 to the negative 6. So whatever you plug into your KSP expression for hydroxide, to what power? The 6th. Whatever you plug in for a concentration of hydroxide to the 6th power, make sure you put in 1 times 10 to the negative 6 for it, because that's its concentration. It might be good not to skip this step, to write it out, because otherwise you might forget exponents and that kind of thing. So what would you put in there? What to the 4th power? You put in 4x. And 1 times 10 to the negative 6 to the 6. And just x. So you'll have the 5th root, which is raising things to the 1 over 5, or raising it to the 0.2. You don't have a 5th root on your calculator. You'll have to raise it to the 1/5 or 0.2. Okay, so we're running out of time here, but anybody get an x?
Yeah, well, 4 times 10.
Oh, what was KSP? 2.3 times 10. I got about 9.8 times 10 to the negative 8.
So you have 2.3 times to the negative 69 equals 4x, or equals x4 minus 10 to the 35, or no?
All right, let's do it into parts so I can see how I got this. It's 2.3 2.3 times 10 negative 69. Huh? Yeah. Oh, you haven't... Didn't I hand them out? Ah!
You handed out some pH.
Oh, we're going to leave them over there and they can pick them up as they walk out. So you can grab, if you did lab already, grab this on your way out. And then grab, did I hand those out?
Yeah, you handed out.
Oh, but I didn't. I handed out the wrong, okay. Yeah, so then and turn that in, make a pile of those. Just fill out the top. Just fill out the top.
What do we solve for?
I gotta get X out of this.
Like, what do we do with that?
You just work it backwards and then
I think it says
plug it back.
it's like the last step.
Yep.
Are you still recording?
Uh-huh. Do you want to have your voice known to the world?
I wouldn't like to get like 3 million hits. It's going to skyrocket as they hear my voice.
Yep. So yeah, the only time you can make it up is Tuesday at 11 a.m.
Tuesday at 11.
Mm-hmm.
I didn't apply the 4x coming into the 4.
You give us an extra one.
Oh, okay. Hey, I did it right.